Okay, for this lecture we're going to do a multi-step problem involving, at first, only reactions from the current chapter. And so we're starting off with an alkyne. It's a terminal alkyne. And we're ending up with a ketone. In this chapter, and before going over the problem, go ahead and attempt this, but try to do it only using reactions from this chapter. After you do that, you should be able to find a way from previous chapters and other reactions we should still know to make this compound in some shorter pathways. Since this is a ketone, in this chapter we really only see one reaction for making ketones, and it's an oxidation reaction. And so this secondary alcohol, as a mixture of enantiomers, since it's a chiral center, can be oxidized up to a ketone using either oxidation reagent. And so one possibility would be to use PCC for this reaction, or since it's a secondary alcohol, you could also use a mixture of sodium dichromate and sulfuric acid, which produces chromic acid. To complete this oxidation. Now, looking at this alcohol, we know a lot of different ways to make alcohols. One way from this chapter to make an alcohol is from an epoxide. And so from this epoxide, we can make selectively this more highly substituted alcohol. This is accomplished through reduction with lithium aluminum hydride. And so the hydride functions as H-, effectively attacking the less substituted carbon of the epoxide. So it's a nucleophilic ring opening with hydride to make this secondary alcohol. And if we're making a mixture of enantiomers, this here would also be a mixture of enantiomers. For your solution, if you just disregarded chirality and just had this as a solid line, that would be perfectly fine. And the same over here, and that would imply a mixture of enantiomers since you didn't designate chirality. From our 5-carbon epoxide here, we don't have a reaction from an alkyne to an epoxide, but we do have a reaction from an alkene to make epoxides. And in fact, the only way we can make epoxides is from reaction with alkenes. And there's 2 different pathways, but we've learned one new one in this current chapter. And so from the terminal alkene, we can use a peroxy acid. And it could be one like MCPBA, or you could have written just the generic R CO3H, which shows the structure or condensed formula of a peroxy acid. But these will then react to make this mixture of enantiomers. From an alkyne to an alkene, this is a reduction, because we're adding bonds to hydrogen. And so this reaction, where we're not completely reducing the alkyne, but we're stopping at the alkene, can be accomplished 2 ways. Because there's no cis or trans designation for a terminal alkyne or alkene, we can use either pathway. And so, for example, you can use sodium metal in ammonia to accomplish this, or alternatively, hydrogen gas and Lindlar's catalyst would do the reaction. And so here, highlighting most of the reactions from this current chapter, we've accomplished this synthesis in 1, 2, 3, 4 steps. Now, how could we do this a lot simpler? Well, from alkyne reactions, we've learned in the past that you can take an alkyne and go directly to a ketone. And this would be a Markovnikov addition, but this could be accomplished most easily in just one step, using a reaction from the alkynes chapter. And that's where we had mercuric sulfate, sulfuric acid, and water. And this goes through an enol intermediate as a reminder. But it's basically Markovnikov addition of water. And so you have water forming a bond to the more highly substituted bond of the alkyne, or carbon of the alkyne, which forms your bond to oxygen. You end up with an enol, which converts to the ketone as the more stable product. Alternatively, once we have an alkene, from the alkenes reactivity chapter, instead of going through an epoxide, of course we can go straight to the alcohol through Markovnikov addition of water. So this would be a shorter pathway as well. And so simply doing Markovnikov hydration would give us that alcohol, which then we could oxidize up with either of these reagents. And so that reviews some older chemistry. Looking at this final molecule as a synthetic target still, though, try and figure out what alkene you could use that upon ozonolysis would give you only this ketone as a product. And so I just want one alkene, and I don't want that alkene to create multiple products, but only give you this ketone. See what you can come up with. Since the ozonolysis reaction will actually cleave the alkene carbon-carbon bond and break those two carbons apart and insert oxygens in there, this backbone must stay the same, except whereas in the product there's an oxygen, the starting material must be an alkene. And so if we just make a symmetrical alkene that looks like this, it can undergo ozonolysis with dimethyl sulfide as a workup step to produce that ketone. Of course, this alkene, for each one molecule, would give you 2 molecules of only that ketone. Alternatively, you didn't have to have the Z configuration. The E would also work. So this molecule also would give you 2 equivalents of that. But anything else would give you multiple products, for example. In this next question, we're looking at dihydroxylation reactions. So what we want to use, or what we want to synthesize as a target, is the following molecule. In this structural drawing, it's a specific enantiomer. Our reaction can make a mixture of enantiomers. What you first notice about this molecule is that it's got hydroxyl groups that are trans to one another, and also the hydrogens are set up trans to one another, and the carbon groups, or the carbon chain, is trans-oriented or anti-oriented, thinking about a Newman projection. And so the other enantiomer would have those same relationships. What we want to think about is how you could make this exact molecule from an alkene starting material. And this might require 1 or 2 steps. When we first approach this, it might be helpful or just good for general review to go ahead and label these chiral centers R and S. So we can see here, this would be our highest prioritized oxygen group, so that'd be priority 1. This carbon bonded to an oxygen would be priority 2, and the other carbon priority 3. So we're going in a clockwise manner, but the hydrogen, the 4th priority group, is coming out at us, so we have to reverse our direction, and that would be S. On the other carbon, if we do go through that same approach, we'd have priority 1, priority 2, priority 3, so we're clockwise. But hydrogen, the 4th priority group, is going back at us, or back away from us, and so it's R. Well, how do we make a trans glycol or trans 1,2-diol? Normally what comes to mind is an epoxide. And so this can be made from an epoxide through a ring opening reaction. And if the alkyl groups are trans in the product, they'll be trans in the epoxide as well. And so this specific epoxide, regardless of whether you use nucleophilic ring opening or acid catalyzed ring opening. So if we use hydroxide and water, that would be nucleophilic ring opening. If you just use H3O+, it would be acid catalyzed. But the stereochemistry of the attack is still the same. Attack must occur from the bottom side, and that gives us that trans relationship. When attack does occur at either carbon, since they're about equally substituted, we'll get trans alcohols, and these groups will also remain trans to one another. And so we'll get this mixture of potential products. As long as we have a mixture of enantiomers here. Well, how do we make this mixture of enantiomers from an alkene starting material? Well, a trans type epoxide would come from a trans alkene. And so we've got, counting our carbons, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and a 6-carbon alkene. So it looks good. Is there another approach that would make this molecule in one step? This one's less intuitive, but you could also make this molecule from the cis alkene. And so if you had the cis alkene, you wouldn't want to go through an epoxide. And we can fill in the reagent up here. It'd be something like peroxyacetic acid. That would form this epoxide. But so we wouldn't want to use that approach if we started with a cis alkene, because then we would get the wrong stereochemistry and we would end up with a diastereomer of this product instead of that mixture of enantiomers. But instead what we can use is osmium tetroxide or potassium permanganate. But these two or those sets of metallic reagents or metal complexes will put both hydroxyl groups, both oxygens on at the same time in the presence of water in a cis fashion because it's a syn addition. And so that would result in a cis 1,2 diol plus its enantiomer. You notice there, obviously, I made a mistake with my number of carbons. Got to have a 6-carbon chain if you're making a 6-carbon product, unless we're adding or taking out carbons. It's always good to double check and count your carbons. This mixture of enantiomers here, then, from the cis-syn addition, although these might look like different products, they're really the same thing. And we can see that if all we do is rotate this 180 degrees around that bond. So if I just do a rotation, so now this group will be up, and our carbon chain is up here. That'll rotate this from coming out at us to being downward, pointing away from us. And so now we can easily see that trans relationship. So the alcohol groups are trans, the alkyl groups are trans, the hydrogens must be trans as well. And so these really are the same thing. So we have 2 different alkenes through 2 different pathways that can give you the same chiral mixture.